Every map of the Milky Way you've ever seen is wrong, catastrophically wrong. Scientists just discovered we've been living in a galaxy twice the size we thought, and somehow missed half of it for 70 years. Wherever you are right now, late night, early dawn, wrapped in blankets, or staring at stars, tonight you're about to find out how we got our own home so spectacularly wrong, and why that mistake just doubled our chances of finding alien life. If that sends a shiver of wonder down your spine, stay and maybe leave a like. Tell me where in the world you're listening from, or follow along for more cosmic mysteries that keep you up at night in the best way. Let's begin. For 70 years, we got it wrong. The Milky Way is not 100,000 light years wide. It is twice that size, maybe more. We have been living inside a galaxy double the scale we taught in every classroom, charted in every textbook, calculated in every paper. This is not a small error, not a rounding mistake, not outdated by a few percentage points, wrong by a factor of 2. Every poster in every classroom shows a galaxy half the actual size. Every documentary animation you trusted, every Wikipedia diagram, every 3D model in every planetarium, all of them display only half of our home. Scientists knew something was off for years. The data came in fragments, hints, anomalies that did not fit the models, stars moving too fast at the edges, satellite galaxies orbiting too far out, mass calculations that never balanced. Then the measurements started pouring in. Gaia spacecraft data, James Webb observations, radio telescope surveys mapping hydrogen clouds at the fringes. Each new instrument revealed the same shocking pattern. The Milky Way extends far beyond where we thought it ended. In 2018, a research team at an Institute of Astrophysics analyzed data from the Gaia spacecraft. Dr. Elena Rossi sat at her desk staring at the screen. Stellar streams orbiting far beyond the defined edge, much farther than they should be. Something's wrong with our numbers, she said. Her first thought: equipment, malfunction, software error. She checked again and again. 3 months of verification. The results never changed. Independent teams ran their own analysis. Same results. The scientific community reacted with skepticism. Impossible. We've measured this for 70 years. Conferences erupted in heated debate. Senior professors refused to accept the findings. Extraordinary claims require extraordinary evidence, but the evidence kept accumulating. From James Webb, from radio telescopes, from gravitational lensing studies, from satellite galaxy observations. By 2020, the pattern became undeniable. By 2023, consensus formed. We had been wrong. Here is the timeline. In the 1950s, astronomers first measured the Milky Way seriously, approximately 100,000 light years across. Through the 1980s and 2000s, they refined the number, still around 100,000s. In the 2010s, the Gaia spacecraft launched, providing the first clues. Between 2018 and 2020, multiple discoveries converged. By 2023, it became official. The Milky Way is at least 200,000 light years across, possibly more. Why does this matter? Everything changes. How we measure the universe. When Andromeda collides with us, whether we are alone. Double the size means double the volume. 8 times more space, actually, since volume increases with the cube of radius. 8 times more stars. 8 times more planets. 8 times more chances for life. Astronomers spent 70 years measuring their own galaxy incorrectly. Sounds terrible, but honestly, this is the most impressive measurement error in history. Not wrong by 10%. Not 20%. wrong by 100%, like confidently saying, "You are 5 feet 7 inches tall, living your entire life with that number," then discovering you are actually 11 feet 4 inches, and everyone was too polite to mention it. Millions of textbooks are now officially obsolete. Books teaching that the Milky Way is 100,000 light years wide. We cannot update them all. They just sit there on shelves, confidently incorrect, like ancient maps showing Earth as flat. Historical value, sure, but do not use them for navigation. Imagine living in an apartment for 15 years. You know every corner, every electrical outlet, every crack in the ceiling. Then one day, you discover a hidden door behind the wardrobe. You open it. Inside is an entire basement, massive, twice the size of your apartment. Staircases, rooms, hallways. It was there the whole time. You just did not know. That is exactly how the astronomy community feels right now. We have been living in the Milky Way, studying it, teaching about it, without knowing half of it existed. You know what? Discovering the Milky Way is twice as large feels like returning to your elementary school at age 20. You remember it as huge, vast, endless hallways. Now it seems tiny, small desks, low ceilings. Except here, it is the complete opposite. Our galaxy is not smaller than memory. It is larger than everything we ever imagined. If we got our own home this wrong, what else did we miscalculate? How many other galaxies are twice as large as we think? What other fundamental assumptions need revision? And tonight, as you lie here, imagine your room suddenly doubling in size. Every wall receding, the ceiling rising, the floor extending, but everything familiar remains. Your bed, your desk, your closet, still there, just now surrounded by so much more space you never knew existed. That is exactly what just happened to our cosmic home. But how did we miss half a galaxy? The answer requires understanding a problem astronomers have wrestled with for a century. The problem is simple. We cannot step outside to look. We are measuring the Milky Way from inside it, trying to map our home while trapped within its walls. Our position makes this nearly impossible. We sit in the suburbs 26,000 light years from the galactic center, inside one of the spiral arms, surrounded by stars, surrounded by dust. We cannot get perspective, cannot see the big picture, like standing in the middle of New York City, trying to draw the city's boundaries. Imagine standing in Times Square. Skyscrapers surround you, neon lights, traffic noise, people everywhere. Now try to figure out where New York City ends. Can you see the edge? No. Can you fly up for a better view? No. You must draw a map based only on what you see at ground level. That is the challenge astronomers face. Cosmic dust blocks our view in almost every direction. The galactic center hides behind thick walls of gas and debris. With optical telescopes, we see maybe 10% of the galaxy. The remaining 90% hides in infrared wavelengths, radio waves, and darkness, like trying to see through dense fog. The old method was simple, but flawed. Astronomers looked in every direction. They found the brightest stars they could see. Where stars thinned out, they drew a boundary. Conclusion: 100,000 light years. Case closed. Except it was never that simple. This method only tracked the bright parts, the obvious parts. It ignored the enormous halo of material surrounding everything. Dark matter extending far beyond visible stars. Faint stars scattered in the outer regions. Gas clouds drifting at the edges. Galaxies do not have sharp edges like dinner plates. They fade gradually. Stars scatter outward in thin streams and clouds. Dark matter, invisible and massive, extends even farther. No clear boundary line exists to draw. Compare this to measuring Andromeda. Easy. Andromeda sits 2.5 million light years away. We see the entire thing at once, edge to edge. We can photograph it, count its spiral arms, map its structure. Measuring the Milky Way is like trying to photograph your own face without a mirror while standing in a fog bank. That is why measurement is so difficult. Trying to measure the Milky Way from inside it is like trying to take a full-body selfie without a mirror, without a selfie stick, without anyone to help in a dark room, while blindfolded. And you have to use an old film camera, cannot check the result. Oh, and you're also spinning. Honestly, it is impressive that scientists got as close as they did over 70 years, only missed half. Pretty good under those conditions. The history of measurement methods reveals how we arrived here. In 1918, Harlow Shapley measured distances to globular clusters. He discovered the sun is not at the galaxy's center. Major discovery, but the measurement was rough. First estimate, approximately 100,000 light years, based on visible stars and limited data. Through the 1950s to 1980s, radio telescopes mapped hydrogen gas. Cepheid variable stars helped measure distances more accurately. Rotation curves revealed strange patterns. Stars moving too fast. The dark matter hypothesis first appeared, but astronomers still focused on the visible disk. From the 1990s to 2010s, the Hubble Space Telescope improved resolution. Infrared surveys saw through dust. Computer simulations modeled galaxy structure. Measurements refined to 100,000 to 120,000 light years, still underestimating the outer regions. Then came 2013. The Gaia spacecraft launched. It tracks over 1 billion stars with unprecedented precision, measures exact positions and motions. The first clues about larger size emerged. Combined with James Webb data, breakthrough arrived. Strange clues accumulated over decades. In the 1970s, stars at the edge moved too fast. Models could not explain it. In the 1980s, satellite galaxies orbited farther than expected. In the 1990s, mass calculations never balanced, always missing something. In the 2000s, stellar streams appeared farther out than the supposed edge. In the 2010s, dark matter models suggested a bigger halo, but nobody trusted the anomalies enough to challenge the 100,000 light-year number. Scientists dismissed them as noise, not signal, until the evidence became overwhelming. Remember the first time you got glasses? If you do not wear them, imagine. Before glasses, you thought you saw everything clearly. Then you put them on. Suddenly, you realized how much you had been missing. Tree leaves are not green blobs. Each leaf is distinct. Distant signs are not colored smudges. They are legible text. That is how astronomers feel when new technology gave them glasses to see the Milky Way properly. Here is an exercise. Stand in a crowd at a concert or festival. Now count how many people are in the crowd. You see those right in front. Maybe a few dozen. People beside you. A few dozen more. But people behind you completely invisible. People far away at the edges cannot see them. You can estimate based on density, but really you are guessing. That is exactly our position in the Milky Way. Standing in a crowd of stars, trying to count how many stars fill the entire galaxy. For decades, these problems seemed insurmountable. Then scientists discovered something unexpected, something that would finally reveal the truth. The breakthrough came from something astronomers had been ignoring for decades: stellar streams, rivers of stars scattered across the sky, crime scenes frozen in time. Stellar streams are exactly what they sound like: streams of stars, long ribbons of light stretching across space. But they are not natural formations. They are evidence of violence, evidence of galactic cannibalism. Millions of years ago, smaller galaxies wandered too close to the Milky Way. Our gravity grabbed them, pulled them apart like taffy. The stars did not vanish. They scattered into long rivers of light orbiting our galaxy in thin streams, remnants of destroyed civilizations, proof that we devoured our neighbors. These streams are galactic crime scenes, bodies left behind after the murder, and they tell the truth about our galaxy's size in ways nothing else can. Here is why stellar streams matter. They follow orbital paths determined by gravity. Every star in a stream moves based on the total mass pulling on it. Measure the stream's path, and you measure the gravitational field. No guesswork, no assumptions. Pure physics. The streams cannot lie. The Sagittarius stream is the most famous. It wraps around the entire Milky Way multiple times, like a ribbon around a gift. Scientists traced this stream across the sky and realized something impossible. It extends far beyond the old galactic boundary. The stream keeps going, and going, and going, which means the Milky Way's gravity keeps going too. Evidence number 1 for a larger size. Then came the GD1 stream, a thin river of stars in the outer halo. Researchers mapped its curve and found something that should not exist. The stream bent in ways that require far more mass than the visible galaxy contains. Either physics is broken, or we are missing something massive. The answer: dark matter. Always dark matter. The streams revealed it like invisible ink under ultraviolet light. The orphan stream haunts astronomers. It orbits so far out that scientists initially thought it occupied intergalactic space, the empty voids between galaxies. Except those voids are not empty. The orphan stream proved the Milky Way's influence reaches farther than anyone imagined. For years, astronomers debated whether it even belonged to us or to some other galaxy. New measurements confirmed it. The stream is ours, which means the Milky Way extends at least that far. Evidence number 2. Have you ever walked on a beach after a storm? Foam seaweed shells form long lines on the sand, traces of waves that pulled them ashore. Stellar streams are like that. They are remnants of gravitational storms that happened millions of years ago. And like those lines on the beach, they tell the story of the force that created them. Pattern after pattern emerged. Each stream discovery added distance to the galactic radius. 5,000 light years here, 10,000 there. The numbers climbed: 120,000 light years, then 150,000, then 180,000. Stellar streams gave astronomers ground truth. You can debate where the visible disk ends. You can argue about where darkness becomes intergalactic space. But you cannot argue with a stream of stars orbiting in formation. Their path is the truth, and the truth kept pushing the boundary outward. 200,000 light years minimum. The streams say so. The math says so. The observations say so. The question is no longer how big is the Milky Way. The question became, how did we miss this for so long? In 2018, Dr. Marion Diericks at MIT analyzed Gaia data on stellar streams. She focused on one stream called PS1A. This stream orbits at a 180,000 light years out. According to old models, this stream should not exist. If the galaxy is only 100,000 light years across, gravity is too weak at that distance. The stream should have dispersed, scattered, gone. But there it was, intact, orbiting perfectly. Either our stream data is wrong, she said, or our galaxy size is wrong. Detecting stellar streams is extraordinarily difficult. Individual stars are barely visible. You must use statistical methods to find the pattern, like staring at static noise and searching for a signal. Gaia tracked 1 billion stars. Computer algorithms identified stars moving together. Same direction, same speed, likely a stream. Dozens of streams discovered this way, each one a piece of evidence. Streams come in two types. Young streams only a few 100 million years old remain coherent and well-defined, easy to trace. The Sagittarius stream is currently being torn apart. We are watching it happen in real time. Old streams billions of years old have dispersed and scattered, harder to detect, completely mixed with halo stars. The remnants of Gaia Enceladus fall into this category. The older the stream, the farther it has spread. But even ancient streams follow predictable orbits, revealing the gravitational field from billions of years ago. What do streams tell us about galactic history? Each stream represents a meal from the past. At least 50 dwarf galaxies devoured. Streams at different distances mark meals at different times. Inner streams are recent meals from the last 1 to 2 billion years. Outer streams are ancient meals from 5 to 10 billion years ago. The pattern shows the Milky Way has always been bigger than we measured. We just could not see the evidence until now. The Milky Way eating dwarf galaxies is like you accidentally eating your roommate's entire bag of snacks. At first you only meant to have a few, then a few more. Then, before you realize it, the whole bag is gone, and you're explaining, but they were so good. The Milky Way is worse. It ate the roommates themselves, the entire galaxy, and never apologized. Streams gave scientists what they desperately needed: undeniable proof. You can dismiss one anomaly, you can ignore two, but dozens of streams all pointing to the same conclusion. You cannot argue with that. The galaxy is twice as large as every textbook claims. The evidence surrounds us. We just needed the right tools to see it. But stellar streams only revealed part of the mystery. The real structure holding our galaxy together remains completely invisible. 90% of the galaxy is invisible. Let that sink in. 90%. Dark matter is not a theory anymore. It is confirmed, measured, mapped. We cannot see it directly, but we see its effects everywhere. Stars orbit too fast. According to visible mass alone, they should fly off into space. Galaxies spin without flying apart. Light from distant objects bends around invisible mass. The evidence is overwhelming. Dark matter exists, and it dominates everything. Think of a skyscraper. You see windows, glass and steel facades, lights in offices, but you do not see the structural frame holding it all up. Steel beams inside the walls, foundation underground, support columns through every floor. The frame is invisible from outside, but without it, the entire building collapses. Dark matter is the frame. Stars are the windows. The frame is far more important than the decoration. The ratio is staggering. Dark matter outweighs visible matter 10 to 1. For every star you see, 10 times more invisible mass exists nearby. This material forms a massive halo around the galaxy, spherical, diffuse, stretching far beyond the visible disk. Old measurements ignored this halo. They focused on bright spiral arms, the glowing core, the obvious features. The galaxy appeared to be 100,000 light years across because that is where visible stars thinned out. But dark matter keeps going. It extends twice as far, maybe more. Think of an iceberg. The visible galaxy is the tip above water. Below the surface sits a mountain of ice 10 times larger. That is the dark matter halo. The true size includes both. Everything you see represents only 10% of reality. Mapping the halo requires gravitational lensing. Light from a distant galaxy passes near the Milky Way. Our dark matter bends it slightly. Measure the bending, and you calculate the mass. The results shocked everyone. The dark matter halo extends to approximately 400,000 light years when counting the faint outer regions. But where does the Milky Way end and intergalactic space begin, where dark matter density drops to half a quarter, a tenth? There is no official edge, just gradual fading into nothing. For practical purposes, astronomers use the virial radius. This marks the point where material is gravitationally bound to the galaxy. Inside this radius, everything orbits together. Outside space is truly empty. For the Milky Way, the virial radius sits around 200,000 to 250,000 light years, double the old estimate, all because of invisible mass. Dark matter is like the air you breathe. You cannot see it, no color, no smell, but it surrounds you, essential for life. Without air, you would know immediately by suffocating. Dark matter works the same way for galaxies. Invisible, but without it, every star would fly apart into space. We live because of something we cannot see. Think about music. When you listen to a song, you notice the melody, the main tune, the lyrics, the chorus. That is the visible part. But underneath there is a bass line, a rhythm section, harmony, things you do not actively notice. But if you remove them, the song collapses. It becomes empty, lifeless. Dark matter is the baseline of the universe. You do not hear it, but it holds everything together. This discovery changes our understanding of galaxies fundamentally. Galaxies are not islands of stars floating in empty space. They are enormous halos of dark matter with stars sprinkled through the center. The visible part is decoration. The invisible part is substance. If our galaxy has this much hidden mass, every other galaxy does too. The universe just got a lot heavier. The discovery of dark matter has a fascinating history. In the 1930s, Fritz Zwicky studied galaxy clusters. He noticed galaxies moving too fast. They should fly apart. He proposed dunkle materie, dark matter. Nobody believed him. They dismissed him as crazy. In the 1970s, Vera Rubin measured rotation curves of galaxies. She found outer stars orbiting as fast as inner stars. Impossible with visible mass alone. Something invisible must be providing extra gravity. Her work finally convinced the scientific community. Through the 1990s and 2000s, evidence accumulated from multiple sources: gravitational lensing observations, cosmic microwave background measurements, large-scale structure simulations. All independently confirmed dark matter exists. It comprises approximately 85% of all matter in the universe. But what is dark matter? We still do not know. The leading hypothesis suggests WIMPs, weakly interacting massive particles. Particles that do not interact with light. They only interact through gravity and possibly the weak nuclear force. Billions pass through your body every second. You feel nothing. They pass through normal matter Like ghosts, deep underground laboratories hunt for dark matter, lux, xenon, others, waiting for a dark matter particle to bounce off a normal atom. So far, nothing detected directly. Either the particles are too elusive, we are looking the wrong way, or dark matter is something else entirely. The mystery remains. Alternative theories exist. Mond suggests gravity works differently at large scales. Perhaps dark matter is primordial black holes from the early universe, or axions, a different type of particle. But the standard dark matter model fits observations best. For now, in the Milky Way, specifically, our halo contains approximately 3.5 trillion solar masses of dark matter, compared to about 400 billion solar masses of normal matter. The ratio is roughly 9-1. Dark matter to normal matter. The halo shape is roughly spherical, slightly squashed. Density is highest at the center and decreases outward, but it extends much farther than stars, like cosmic scaffolding, holding the galaxy together. The implications are profound. We live in a galaxy made mostly of something we cannot see. 90% of everything around us is invisible. We cannot touch it, cannot detect it directly. We only know it exists because of gravity. You think you know where you live. You are swimming in an ocean of dark matter, and you cannot feel the water. We have traveled halfway through this story now. From the initial shock that our galaxy is twice as large as we thought, to understanding why we measured wrong, to seeing evidence from stellar streams, and now to dark matter, the invisible force comprising 90% of reality. Each section is a layer of revelation, and we have not yet reached the most startling part. What does all this mean for our future? That comes next. With the true size revealed and the invisible structure exposed, one question remains. What are the consequences of living in a galaxy twice as large as we believed? The star count just doubled. 400 billion stars. Not 200 billion like we thought. 400 billion. The number is incomprehensible. If you counted one star per second, it would take 12,700 years to count them all. Longer than recorded human history, and you would still have billions left. 400 billion opportunities for planets. 400 billion chances for life. More stars means more planets, means more habitable zones. Conservative estimates suggest 60% of stars have planets. That gives us 240 billion planetary systems. Maybe 10% orbit in the habitable zone where liquid water can exist. 24 billion potentially habitable planets, doubled from previous estimates. Even if life is rare, 1 in 1,000 habitable planets, that still gives us 24 million living worlds in the Milky Way alone. 24 million planets where biology exists, where cells divide, where evolution operates, where organisms adapt and survive. Even if intelligent life is extraordinarily rare, 1 in a million among living worlds, that gives us 24 intelligent species in our galaxy. Maybe more, maybe less. The Drake equation just changed. Every variable increased. The probability of finding alien life went up significantly. But here is where it gets strange. 400 billion stars, doubled chances for life. Where is everybody? The Fermi paradox intensifies. If there are so many chances for life, so many potential civilizations, why no signals? Why no alien probes? Why does the galaxy seem empty? Possible answers exist. Perhaps the great filter lies ahead of us or behind us. Perhaps intelligence is extremely rare. Perhaps civilizations self-destruct. before achieving interstellar communication. Perhaps they exist, but choose not to communicate. Perhaps we are listening the wrong way. Better odds now, but still no contact. The mystery deepens. The Andromeda collision timeline shifted. Old calculations said 4.5 billion years until impact, but a bigger Milky Way means bigger gravitational reach. The galaxies will start affecting each other sooner, maybe 4 billion years, maybe less. Dark matter halos might already be touching. The collision may have already begun, invisibly, slowly, in the dark matter realm where we cannot see. Your descendants, if humanity survives, that long will watch Andromeda growing larger in the night sky. Eventually, it will fill half the visible sky. The galaxies will dance around each other. Multiple passes over 1 billion years. Then the final merge into Milkomeda, one massive elliptical galaxy, the combined remnant of 2 ancient spirals. Mass calculations tripled. The old estimate said 1.5 trillion solar masses. The new estimate is 4 trillion solar masses, maybe more. Triple the mass appeared in the data. Not that the galaxy gained weight. It was always there. We just could not measure it correctly. Most of the extra mass is dark matter, but also more visible stars than we thought. More gas, more dust, more everything. Bigger galaxies mean deeper gravitational wells, harder to escape from. When material gets pulled into tidal tails, during collisions, more of it falls back. The merger timeline stretches longer, more orbital passes before the final merge, more complex interactions, more violent star formation bursts, a larger, final merged galaxy. The relationship between the Milky Way and Andromeda changed. Andromeda was always considered the bigger sibling, the alpha galaxy of the local group. But new measurements suggest we might be equals, both approximately 4 trillion solar masses, 2 galactic superpowers on a collision course. Not David versus Goliath, more like Godzilla versus King Kong. Our cosmic address needs rewriting. Local group boundaries changed. The space between galaxies is smaller than we thought. Gravitational influence reaches farther. Some dwarf galaxies we considered independent are actually satellites. Territory has been redistributed. Our galactic empire is larger than we realized. CT, the search for extraterrestrial intelligence, scanned approximately 100,000 stars so far. Under the old model that represented 0.05% of the galaxy, now it represents only 0.025% of the new galaxy. We have barely begun searching. We need to scan 4 times more volume. Telescopes like the Allen Array and FAST in China are ramping up efforts, but doubling the search space means exponentially more time needed. The James Webb Space Telescope is studying exoplanet atmospheres, looking for biosignatures, oxygen and methane combinations that suggest life. The original target list included approximately 1,000 planets. Now, astronomers realize there are twice as many candidate systems. Each star could have multiple planets. Priority targets need re-evaluation. More work, but more opportunities. Galaxy formation models need complete overhaul. Computer simulations predicted Milky Way-sized galaxies based on the old size. Now, the models need to run again with the correct mass and correct size. How does this affect when the galaxy formed? How many mergers it experienced? Star formation history. Everything needs recalculation. The economic impact on astronomy is significant. Textbooks need reprinting. Planetariums need new shows. Educational materials are outdated. Research papers need revisions. Grant proposals need rewriting. Not a crisis, but substantial. Like when Pluto was demoted from planet status. Except on a much bigger scale. Scientists now must rewrite thousands of papers. Every paper, referencing Milky Way 100,000 light years, needs correction. Imagine using find and replace. Search for 100,000 and replace with 200,000 thousands of times. And they cannot say, well, the old number is close enough. No, science does not work that way. They must fix everything. This might be the biggest undo in the history of science. The universe has no Control-Z button, but humans must do it manually. The philosophical implications run deep. We have been wrong about home for 70 years. What else are we wrong about? This is a humility lesson for science. It shows we must always question, always verify. No measurement is truly final. The universe constantly surprises us. The more we learn, the more we realize we do not know. You know that feeling when you suddenly realize the world is bigger than you thought. The first time you saw the ocean. The first time you flew in an airplane and looked down. The first time you saw a photograph of Earth from space. Each time your perspective shifts, you realize you are smaller, but simultaneously, the possibilities are larger. That is this feeling. Our home, the Milky Way, just doubled in size. We just became smaller, but our chances of finding friends beyond Earth just doubled too. But there is a hopeful note in all this. A bigger galaxy means more chances for life, more potential civilizations, greater probability we are not alone. Somewhere orbiting one of those 400 billion stars, life might be looking back, wondering the same questions, feeling the same loneliness, hoping for contact. And now the odds are better. Double the chances, double the hope. The implications cascade through every field of astronomy. Stellar population studies need revision. Galaxy morphology models need updating. Active galactic nuclei theories need adjustment. Supermassive black hole evolution timelines need recalculation. Everything connects to galaxy size. Distance measurements to other galaxies become uncertain. If we measured our own galaxy wrong, we probably measured others wrong too. The cosmic distance ladder, the method we use to measure the universe, sits on shaky foundations. Every rung needs checking. Every measurement needs verification. Dark energy calculations shift. They depend on accurate mass measurements. More matter means more gravity. More gravity means the universe should expand slower. But expansion rates measured independently show no change. So, either dark energy is stronger than calculated or distributed differently, or our entire dark energy model needs revision. The Hubble tension worsens. This is the disagreement between different methods of measuring the universe's expansion rate. Local measurements using supernovae give one answer. Cosmic microwave background. Measurements give another. Now, with galaxy sizes doubled, the discrepancy grows larger. Something fundamental is wrong with our cosmological models. Barrier acoustic oscillations, ripples, in the distribution of galaxies serve as standard rulers for measuring cosmic distances. But these ripples depend on galaxy clustering. How massive galaxies are, how they distribute. If galaxies are bigger and more massive, the clustering changes. The ripples shift. The standard ruler gets adjusted. Distance measurements need recalculation. Dark energy estimates shift accordingly. Every spiral galaxy in the universe is probably twice as large as recorded. Andromeda grew from $220,000 to over 300,000 light years. Triangulum expanded from 60,000 to nearly 100,000 light years. Every major galaxy examined came back larger. The pattern is universal. We systematically underestimated spiral galaxy sizes across the board. The universe becomes denser, more crowded. Galaxy collision rates increase. The space between galactic groups shrinks. The hierarchy of cosmic structure shifts at every level. Superclusters reorganize. The cosmic web needs redrawing. For the search for life, this changes everything. Not just double the stars, double the planets, double the habitable zones, but also double the time, double the volume to search. SETI efforts, already daunting, become twice as daunting. But the payoff, if we find something, becomes twice as meaningful. The night sky will look different to future generations. When astronomers map the complete Milky Way, when they chart all 400 billion stars, when they identify every stellar stream and satellite galaxy, the picture that emerges will be magnificent. A galaxy far grander than we imagined. Our home revealed in its true scale. Children born today will grow up learning different numbers in school. 200,000 light years. 400 billion stars. These will be facts as basic as the Earth orbiting the Sun. They will wonder how we got it so wrong for so long, and we will tell them we measured from inside. We did the best we could with the tools we had, and when better tools arrived, we corrected our mistake. That is science. Not about being right forever, about being willing to be wrong and correct yourself when evidence demands it. This story, this revelation about our galaxy's true size, represents something larger than astronomy. It represents human curiosity, our drive to understand our place in the cosmos, our willingness to question everything, even things we thought we knew for certain. We live in a galaxy twice as large as we believed yesterday. That makes us smaller, more insignificant, a tiny speck in a vast machine. But it also makes us remarkable, because we figured it out. We, these tiny specks, these brief flickers of consciousness on a small planet, somehow measured the invisible scaffolding holding our galaxy together. We discovered we were wrong and had the courage to admit it. That is worth celebrating. And as you close your eyes tonight, know that your cosmic home just grew larger. 400 billion stars are shining in the darkness, each one a world unto itself, each one with its own story. And somewhere on a planet orbiting one of those stars, someone might be lying down, looking up at their sky, wondering if they are alone. Now we know there is double the chance they exist. And that thought that we might not be alone, that the universe is bigger and fuller than we imagined, is a warm thought to carry into sleep. Breathe deeply, relax. Let the stars, all 400 billion of them, sparkle in your dreams. The Milky Way is not alone. Dozens of smaller galaxies orbit around us like moons around a planet. We call them satellite galaxies, and they just rewrote our cosmic address. The Large Magellanic Cloud is the biggest visible from the southern hemisphere as a cloudy smudge in the night sky. It contains 30 billion stars. The Small Magellanic Cloud sits nearby with 7 billion more. Then come the dwarf galaxies: Sagittarius Dwarf, Draco Dwarf, Ursa Minor Dwarf, each one a miniature galaxy with its own stars, its own history, its own orbit. For years, scientists treated these satellites as neighbors, separate objects passing by, independent travelers in the cosmic void. But new measurements revealed the truth. They are not passing by. They are trapped, bound to us, prisoners orbiting within the Milky Way's gravitational sphere of influence. This discovery changed everything. When you measure how fast a satellite orbits, you can calculate the mass holding it in place. More mass means tighter orbits. Less mass means objects drift away. The satellite galaxies orbit at specific distances and speeds that reveal our total gravitational pull. The Large Magellanic Cloud sits 160,000 light-years away. It orbits the Milky Way once every 1.5 billion years. For it to stay in that orbit at that distance, our galaxy must be massive. Far more massive than old estimates suggested. Researchers tracked dozens of satellites and found the same pattern. They all orbit farther out than expected. They all move faster than predicted. The only explanation: the Milky Way is bigger and heavier than we realized. But the real breakthrough came from tidal streams. When a satellite galaxy orbits too close, the Milky Way rips it apart. Stars get pulled away in long trails. The Sagittarius dwarf is currently being destroyed this way, right now, in real time. We are watching it happen. Its stars stretch across the sky in a stream wrapping around the entire galaxy. These tidal tails act as test masses. They show where the gravitational field is strongest, where it weakens, where the boundary sits. Map enough tidal streams, and you map the edge of the galaxy. What scientists found shocked them. The streams extended far beyond the supposed galactic edge. Some reached past 150,000 light-years. Others hit 200,000. A few hints suggested material even farther out. The satellites were screaming the truth. The Milky Way is huge. This had immediate implications. If our galaxy is this large, the local group of galaxies needed redrawing. The space between us and Andromeda is smaller than we thought. The gravitational influence of each galaxy reaches farther. Collisions happen sooner. Mergers start earlier. Every satellite galaxy became a data point. Every orbit a measurement tool. Together, they painted a picture of a galactic giant, not the medium spiral we imagined. Some satellites orbit so far out, we are still discovering them. Every few years, astronomers find another dwarf galaxy hiding in the data. Each new discovery extends our boundary a little farther. How many more are out there? How much bigger does the Milky Way actually get? Discovering these satellites took decades of patient observation. They are incredibly faint. The dwarf galaxies contain maybe a few million stars, compared to our hundreds of billions. Finding them is like searching for a candle flame next to a spotlight. Early discoveries came from photographic surveys. Astronomers took long exposure images of the sky and looked for fuzzy patches that might be distant galaxies. Some turned out to be satellite dwarfs orbiting nearby: the Sculptor dwarf, the Fornax dwarf, the Carina dwarf. Discoveries through the 1930s to 1970s. Modern digital surveys revolutionized the search. The Sloan Digital Sky survey mapped a quarter of the sky in unprecedented detail. Hidden in that data were dozens of ultra-faint dwarf galaxies, so dim that individual stars barely registered. Only statistical analysis revealed their presence. The algorithms searched for overdensities, regions with slightly more stars than random chance would predict. When you find a cluster of stars, all at the same distance, all moving together, you have found a satellite galaxy. Most are so faint you cannot see them with the naked eye. You need computer analysis of millions of data points. The Sagittarius dwarf has a particularly tragic story. Discovered in 1994, surprisingly late given its size, it sits on the opposite side of the galactic center from us, hidden behind the densest star fields. For years, astronomers thought it was just part of the Milky Way. Then they measured the velocities of its stars, all moving together, a coherent group, not random halo stars, but a galaxy in its death throes. The Milky Way's gravity is tearing it apart. Each orbit brings it closer. Each pass strips away more stars. Scientists tracked its orbital history backward. About 8 to 9 orbits ago, it was intact, a functioning dwarf galaxy with its own identity. Now, it is a scattered stream. In a few billion years, no trace will remain, except scattered stars mixed into our halo, former citizens of a destroyed civilization, now ours. The Magellanic Clouds face a similar fate. They orbit close enough, the tidal forces are already pulling gas away. The Magellanic stream, a ribbon of hydrogen gas, trails behind them for 600,000 light years. This gas will eventually fall into the Milky Way. The clouds themselves will be consumed, maybe in 2 billion years, maybe 3. Gravitational calculations show their orbits decaying. Each pass brings them closer to the galactic disk. Eventually, they will cross through it. The collision will be spectacular. Violent star formation, disruption of spiral arms, then absorption. They are doomed. It is like discovering your neighbors. The ones you thought were just visiting actually belong to your family, not by choice, by gravitational capture. They cannot leave. They are bound to us, and eventually, they will become part of us. The Milky Way collecting satellites is like someone collecting Pokemon. Gotta catch 'em all. Except instead of cute creatures, it is entire galaxies. And instead of catching them voluntarily, gravity does it automatically. And instead of keeping them in Pokeballs, we slowly tear them apart and absorb their stars. Okay, maybe not the best comparison, but the collecting instinct is there. Many dwarf galaxies we once considered independent are actually satellites. They orbit in regions claimed by the Milky Way's gravitational field, territory we did not know we controlled. As measurements improved, the list of satellites grew. 20 satellites, 30, 40, over 60 confirmed now, and probably hundreds more waiting to be discovered, each one proof of our extended reach. Some satellites sit in the space between us and Andromeda. Which galaxy do they belong to? The answer is complicated. They orbit in the combined gravitational field of both. They feel pulls from multiple directions. As the Milky Way and Andromeda approach each other, these dwarf galaxies will get caught in the middle, torn apart, scattered, casualties of a galactic war. The satellites revealed something fundamental about galaxy structure. The visible disk we see is not the whole story. The gravitational influence extends much farther, like roots of a tree spreading underground, far beyond the visible trunk and branches. You cannot see the roots, but they define how large the tree really is. Satellite galaxies are those roots made visible. They trace the invisible gravitational field. They mark the true boundaries of our cosmic home. And those boundaries are vast, far vaster than 7 decades of astronomy suggested. The satellites orbiting 150,000 light years out 200,000 light years out, they are all bound to us, all part of our system, all evidence of a galaxy twice as large as we thought. The satellites showed us how far our gravity reaches, but they also revealed something strange about how stars move within that gravitational field. The galaxy is spinning too fast. It should fly apart. Stars at the outer edge orbit at speeds that make no sense. They should escape into intergalactic space. They should obey Kepler's laws of motion. They should slow down as you move away from the center. They do not, and nobody fully knows why. In our solar system, planets farther from the sun orbit slower. Mercury races around in 88 days. Earth takes 365 days. Neptune takes 165 years. The farther out you go, the weaker the sun's gravity, the slower the orbit. This is basic physics. Isaac Newton figured it out 300 years ago. Galaxies should work the same way. Most of the mass sits near the center. Stars farther out should feel weaker gravity. Their orbits should slow down. When you measure their speeds, you should see a nice curve, decreasing with distance. Except that is not what happens. Stars at the edge of the galaxy orbit at nearly the same speed as stars closer in. The rotation curve stays flat. This is impossible unless there is more mass out there than we can see. Dark matter, always dark matter. The invisible halo provides the extra mass. It extends far beyond the visible stars, keeping outer objects moving fast. The flat rotation curve is the smoking gun, the proof that dark matter exists in huge quantities. But even accounting for dark matter, the speeds are higher than predicted. Some stars in the outer halo move at 130 miles per second. Others hit 150. These velocities are barely below escape velocity. The stars are almost fast enough to leave the galaxy entirely. Why do they orbit so close to the edge of escape? What fine-tuned mechanism keeps them bound but barely? This is called the escape velocity problem, and it haunts astronomers. Think of a rope swing spinning in circles. The person on the outer edge swings fastest. If they go too fast, the rope cannot hold them, and they fly off. Galaxy stars at the edge are like that person spinning at the absolute limit before flying away. But somehow they stay attached. Somehow the rope holds. One possibility is that we still underestimate the galaxy's mass. Maybe there is even more dark matter than current models suggest. Maybe the halo is denser at the edges than we think. Maybe our mass calculations are still wrong, even after all the corrections. Another possibility is that the galaxy recently grew. If the Milky Way devoured a large dwarf galaxy in the past few billion years, the merger could have injected stars into fast orbits. These stars have not had time to settle into stable paths. They still carry the energy from the collision. They are cosmic immigrants moving differently than native-born stars. Evidence supports this idea. The Sagittarius dwarf is being torn apart right now. Its stars are scattering into the Milky Way's halo at high speeds. In a billion years, those stars will look like native halo stars. Fast, barely bound, mysterious. Future astronomers might puzzle over them without realizing they came from a devoured galaxy. But what comes next is even stranger. Some stars move too slow. Hypervelocity stars in reverse. Objects that should orbit faster based on their location, but do not. They drift along like they are trapped in molasses, like swimmers trying to move through honey. Nobody has a good explanation for these either. The rotation curve should be simple. Measure speeds calculate mass, everything fits. Instead, every new measurement reveals more anomalies, more outliers, more stars doing things they should not be able to do. Vera Rubin discovered this problem in the 1970s. She measured rotation curves of spiral galaxies and found them all flat, stars at the edges moving as fast as stars near the centers. She presented her findings at conferences. Most astronomers dismissed her. "Your measurements must be wrong," they said. "Check your equipment. Everyone knows rotation curves should decline." She checked, measured again. Different galaxies. Same result. Flat rotation curves everywhere. The astronomical community resisted for years. Dark matter seemed too strange, too convenient, too much like adding invisible fudge factors to make the math work. Then other researchers confirmed her findings independently. Different telescopes, different methods, same flat curves. The evidence became overwhelming. Rotation curves are flat. Dark matter must exist. Rubin's persistence changed astronomy. She forced the community to accept an uncomfortable truth. Most of the universe is invisible. We see only a tiny fraction of what exists. The rotation curves proved it beyond doubt. How do astronomers measure rotation curves in practice? They use the Doppler effect. When an object moves toward you, its light shifts blue. When it moves away, its light shifts red. By measuring the red shift and blue shift of stars at different distances from the galactic center, you can calculate how fast they orbit. For the Milky Way, this is complicated. We sit inside the galaxy, moving with it. Our own motion through space adds to or subtracts from the motion we measure. Separating our velocity from the star's velocities requires careful calculations. You need to know exactly where we are and how fast we are moving. Radio telescopes mapping hydrogen gas help enormously. The gas follows the same rotation curve as stars, but is easier to detect in the outer regions where stars are sparse. Hydrogen emits radiation at a specific wavelength, 21 centimeters. By measuring the Doppler shift of this radiation, you map the rotation curve to enormous distances. Computer simulations predict what rotation curves should look like based on visible mass alone. The predictions show a declining curve, faster near the center, slower at the edges, like planets in the solar system. The actual observations show a flat curve, same speed everywhere. The discrepancy is enormous. You need 10 times more mass than visible stars provide to explain the observations. That missing mass is dark matter. Recent discoveries made the mystery worse. In 2023, astronomers found stars at the very edge of the galaxy moving at 180 miles per second. At that distance, 200,000 light years out, they should be moving maybe 90 miles per second based on visible mass. Even with dark matter models, they should be moving around 120 miles per second. But 180, that requires even more mass than current models include. Either the dark matter halo is more massive than calculated, or it extends farther than predicted, or it is distributed differently than models assume, or something else is accelerating these stars that we do not understand yet. You know that feeling when you press the accelerator in your car, but you are not sure if you have enough gas to reach your destination. That anxiety of running on empty while still going fast. The engine revving, but the fuel gauge hovering near zero. That is what these edge stars feel like. Going incredibly fast, barely enough gravity to keep them from flying away, running on cosmic fumes. The rotation curve reveals something profound about galactic structure. What you see is not what you get. The bright stars, the glowing gas, the obvious features represent a tiny fraction of the total mass. The rest hides in darkness, invisible scaffolding, holding everything together. The galaxy is a magic trick. The visible parts distract you, while the invisible parts do the actual work. Different dark matter models predict different rotation curves. Warm dark matter produces smoother profiles. Cold dark matter creates lumpier structures. Self-interacting dark matter behaves differently in galactic cores. So far, cold dark matter fits best, but the fit is not perfect. Discrepancies remain. Small ones, nagging ones, the kind that might point toward new physics or might just be measurement error. Scientists cannot tell yet. Physics works everywhere else in the universe. It works in solar systems, in star clusters, in galaxies far away. But in our own backyard, in the Milky Way's rotation curve, something is still not quite adding up. Stars move faster than they should. The galaxy holds together when it should not, and the larger size makes the problem worse. More volume means more stars at greater distances, more weird velocities to explain, more discrepancies between prediction and observation. The bigger Milky Way revealed deeper mysteries about how galaxies work. We measured the size correctly now, but we still do not fully understand the forces holding it all together. Rotation curves showed us stars moving strangely, but the overall structure, the grand design of spiral arms, holds even more secrets. The Milky Way has 4 major spiral arms, or maybe 5, or maybe 6. Astronomers are still arguing about it. After 70 years of studying our own galaxy, we cannot even agree on the most basic structural question. How many arms does it have? The old model was clean and simple. 4 major spiral arms: Scutum Centaurus, Norma, Sagittarius, Perseus. Each arm a river of stars, gas and dust, spiraling outward from the galactic center. These arms trace regions where new stars are born. Bright, dense, easy to spot. Then better telescopes arrived. Infrared instruments that see through dust. Radio telescopes that map hydrogen gas. Space-based observatories above atmospheric interference. Each new tool revealed features we missed before. The far 3 kiloparsec arm appeared first, a minor spiral arm hiding behind the galactic core. We could not see it with optical telescopes because the center blocks the view. Too much dust, too many stars. But infrared instruments cut through the obscuration. There it was, an entire arm thousands of light years long, right under our noses. Then came hints of other structures. The local arm, where our solar system sits, might actually be a major arm, not just a minor spur. New observations suggest it connects to larger structures farther out. What we thought was a branch might be a whole limb. The outer arm posed another mystery. It sits at the extreme edge of the visible galaxy. Some researchers thought it was just scattered stars, no real structure, but detailed mapping revealed organized spiral patterns extending far into the outer regions. The galaxy has structure where we thought it was empty, but here is the truly bizarre part. Nobody knows how spiral arms form. We see them in almost every disk galaxy, beautiful, elegant spirals, but the physics behind them remains murky. Here is the problem. Stars orbit the galactic center at different speeds. Inner stars orbit faster. Outer stars orbit slower. If spiral arms were just concentrations of stars, they would wind tighter and tighter over time, like stirring cream into coffee. The pattern swirls, mixes, disappears. Within a few rotations, the arms should blur into a smooth disk. They do not. Spiral arms persist for billions of years. This suggests they are not material structures. They are the density waves, regions where stars temporarily bunch up, creating the illusion of an arm. Like a traffic jam. Cars move through the jam, but the jam itself stays in place. The slowdown propagates backward through traffic even as individual cars move forward. Spiral arms work the same way. Stars move through the arms. As they enter the dense region, they slow down slightly. Gravity from all the nearby stars pulls on them. They spend more time in the arm than outside it. This creates a persistent pattern. The arm appears stationary, even though the stars constantly flow through it. Density wave theory works mathematically, but observations keep finding exceptions. Some arms have too many young stars. Others show gaps where stars should be. The outer arm appears too massive to be just a wave. It might be real structure. Material pulled out during a galactic collision millions of years ago. The bigger Milky Way size complicates everything. More space means more room for structure. Arms can extend farther. New arms can form in regions we thought were empty. The spiral pattern becomes more complex. Recent surveys using the Gaia spacecraft mapped 1 billion stars with incredible precision. The data revealed substructure within the arms, branches, spurs, gaps. The spiral pattern is not clean. It is messy, chaotic, like tree branches growing in every direction. Some researchers now argue the Milky Way is not a grand design spiral at all. It might be a flocculent spiral, a galaxy with patchy, poorly defined arms. Grand design spirals have clear symmetric arms. 2 major arms, maybe 3 wrapping smoothly around the center. Flocculent spirals have many fragmentary arms, messy, asymmetric, like foam on ocean waves. This would explain why different surveys find different arm counts. Everyone sees different features, depending on what they measure. Infrared surveys see dust lanes. Radio surveys see gas. Optical surveys see bright stars. Each reveals a different piece of the structure. Put them together, and you get confusion. Astronomers still argue at conferences. 4 arms. No 5? Actually, the local arm should count as major, so 6. The debate continues. More telescopes, more data, more arguments. It is somewhat embarrassing. We cannot agree on the basic structure of our home, like living in a house for decades and arguing about how many rooms it has. I count 5 bedrooms. No, that closet is too big, it's 6. Meanwhile, the house just sits there unchanged while we bicker. The humor is not lost on astronomers themselves. At a conference in 2022, a presenter started with, "Today I will argue the Milky Way has exactly 4.7 spiral arms." The audience laughed. Then he showed the data. He was serious. The truth lies somewhere between discrete categories. Not 4, not 5, something in between depending on how you define an arm. Infrared telescopes revolutionized our understanding of spiral structure. Dust blocks optical light, but glows in infrared. By mapping the dust, you map the dense regions where stars form. The Spitzer Space Telescope did this for the Milky Way. Its images revealed spiral arms we never saw before. Arms hidden behind the galactic center. Arms too dusty for optical observation. The persistence of spiral arms remains mysterious. Density wave theory provides one answer, but not the complete answer. Computer simulations show spiral patterns, forming naturally in rotating disks. Gravitational instabilities create waves. The waves propagate. Arms appear. But simulations also show the patterns should change over time. New arms form. Old arms fade. The structure should be dynamic, not static. Maybe that is what we see. Maybe the Milky Way's messy structure reflects this dynamic process. Arms forming, arms dissolving, constant flux over billions of years. We see a snapshot, a moment frozen in time. The galaxy looked different a billion years ago. It will look different a billion years from now. The outer arm is particularly puzzling. It contains a lot of mass, too much for a simple density wave. Some researchers propose it formed during a past merger, when the Milky Way collided with a large dwarf galaxy billions of years ago. The interaction pulled material into a long tidal tail. That tail eventually settled into an orbit. Now it looks like a spiral arm, but it is actually merger debris. This idea fits with the galactic cannibalism story. The Milky Way grew by eating smaller galaxies. Some of those meals left traces, tidal streams, stellar shells, and maybe spiral arms that are not really spiral arms at all, just scars from ancient violence. The local arm, our home, became more interesting with better data. Originally classified as a minor spur between the Sagittarius and Perseus arms, new measurements show it is substantial, dense, long. It might deserve promotion to major arm status, which would make the Milky Way a 5-arm spiral instead of 4-arm. Unless you count the other minor spurs, in which case maybe 6 or 7, you see the problem. The more carefully we look, the more complicated the structure becomes. The neat textbook diagram with 4 symmetric arms is fantasy, a simplified cartoon. Reality is messy. Spiral structure affects star formation. Arms are where gas clouds collide and compress. Compression triggers collapse. Collapse forms stars. The arms light up with newborn stars, bright and blue. These stars do not live long, maybe 10 million years. They die before they drift out of the arm. This keeps the arms bright and obvious. But between the arms, star formation slows. Gas spreads out. Density drops. Fewer collisions mean fewer new stars. The inter-arm regions appear darker, not because they lack stars, but because they lack young bright stars. Our sun sits in the local arm. We orbit within a spiral feature, not at the brightest part, but close enough. The solar system completes one orbit around the galaxy every 230 million years. During that time, we cross through different spiral arms. We pass through dense regions and sparse regions. This affects our environment. More nearby stars when crossing arms, fewer stars between arms. Some researchers propose a connection between spiral arm crossings and mass extinctions on Earth. The idea is controversial but intriguing. When the solar system crosses through a dense spiral arm, gravitational perturbations could shake up the Oort cloud. Comets get knocked loose. Some fall toward the inner solar system. Impact rates increase. Mass extinctions follow. The timing almost matches. The dinosaurs died 65 million years ago. We were crossing through an arm around then. The Permian extinction 250 million years ago also lines up roughly with an arm crossing. But the correlation is not perfect. Many arm crossings produce no extinctions. Many extinctions happen between arm crossings. The connection remains speculative. Still, it is a reminder. Galactic structure affects us. We think of the Milky Way as distant, abstract, irrelevant to daily life. But we live inside it. It shapes our cosmic environment. The spiral arms influence where stars form, where planets form, where life might emerge. Structure matters. Spiral arms showed us visible structure, beautiful but confusing. But an even deeper mystery lurks in what we cannot see, matter that should exist but has vanished. There is mass we cannot account for, material that should be there but is not. Astronomers call it the missing baryon problem, and it just got 3 times worse. Here is the issue. When you add up all the visible matter in the galaxy, you get about 200 billion solar masses. Stars, planets, gas clouds, dust, everything we can see. Then you check the cosmic ratios. Simulations say galaxies should contain a specific amount of baryonic matter based on how the universe evolved. Baryons are normal matter, protons, neutrons, atoms, the stuff we are made of. But when we count stars' gas and dust, we come up short, way short. About half the expected baryons are missing. Where did they go? This is not dark matter. Dark matter is a separate mystery. We know it is there because of gravitational effects. The missing baryons are regular matter, normal atoms. They should be somewhere, but we cannot find them. Several possibilities exist. Theory 1 suggests the missing baryons were ejected. Supernovae explode, stars produce powerful winds, active galactic nuclei blast out material. Over billions of years, this outflow could have expelled enormous amounts of gas into intergalactic space. The baryons are not missing. They are just outside the galaxy now, too diffuse to detect easily. Theory 2 proposes the baryons are hiding. Maybe they exist as cold gas clouds, too faint to see, or as dim brown dwarfs, too small to shine, or as rogue planets drifting through interstellar space, or as dust grains, too small to detect individually. They are there. We just cannot find them with current instruments. Theory 3 gets weird. Maybe the baryons were never in the galaxy at all. Maybe they are stuck in the intergalactic medium. The space between galaxies contains thin gas, extremely thin, but across enormous volumes, it adds up. Perhaps half the universe's baryons are floating in this medium, never falling into galaxies, like baking a cake, but realizing you are missing half the flour. Where did it go? Did someone take it? Did you forget to buy enough? Is it hiding in a cabinet you have not checked? The mystery is frustrating because the ingredients should be here. The recipe requires them, but they are gone. Recent observations favor Theory 1. X-ray telescopes detected hot gas halos around galaxies. This gas is too hot to form stars, but too diffuse to see easily. It exists in a weird intermediate state, ionized, energetic, invisible to most instruments, but it is there, and there is a lot of it. When scientists measured these hot halos, they found significant mass, enough to account for much of the missing baryons. Maybe the problem was solved, except the Milky Way just got bigger, which means it should have even more baryons, and we still cannot find them all. A 4 trillion solar mass galaxy needs a specific amount of normal matter based on cosmic ratios, about 400 billion solar masses of baryons. We see maybe 200 billion in stars and gas, the rest missing. Again, tripling the galactic mass tripled the missing mass problem. If the galaxy is twice as wide and much more massive, where did all that extra baryonic matter go? It should be somewhere. In the halo, in the disk, in orbit. But we cannot find it. Some researchers suggest the dark matter halo traps hot gas at enormous distances, hundreds of thousands of light years out. This gas is so hot and diffuse that current X-ray telescopes barely detect it, but it carries significant mass. Future missions with better sensitivity might reveal enormous reservoirs of missing baryons hiding in plain sight. Another possibility involves the circumgalactic medium, the zone around the galaxy where material cycles in and out. Gas ejected by supernovae flows outward, cools, falls back. This recycling process creates a massive reservoir of baryons surrounding the galaxy. Not quite inside, not quite outside, transitional. The James Webb Space Telescope is hunting for these baryons now. Its infrared sensitivity can detect warm gas that other instruments miss. Early results hint at more material in the outer halo than previous surveys suggested. But we need more data, more observations, more time. You know that feeling when you balance your bank account and realize you're missing a large sum. You check the deposits, check the withdrawals, add everything twice. The numbers do not match. Money disappeared. You feel panic, confusion. Where did it go? Astronomers feel that way about baryons. The cosmic budget does not balance. Matter is missing. The numbers say it should be here. We cannot find it. The bigger galaxy makes this worse. More volume means more places for baryons to hide. More distant regions we cannot observe well. More material in forms we cannot detect. The problem scales with size. Here is the unsettling truth. We live in a galaxy where we cannot account for half the normal matter. We know roughly where the dark matter is. That is the easy part. But regular matter, the stuff we are made of, the atoms comprising the stars, planets, and people, half of it keeps hiding from us. A bigger galaxy means a bigger mystery, more missing mass, more unanswered questions, and somewhere in the darkness, 200 billion solar masses of normal matter are waiting to be found. Think about the scale. 200 billion solar masses. Each solar mass is twice times 10 to the 30th power kilograms. Multiply that by 200 billion. The amount of missing matter is incomprehensible. More mass than all the stars we can see. Just gone, vanished, hiding. The circumgalactic medium might hold the answer. This region extends from the visible edge of the galaxy out to several 100,000 light years. Material in this zone is neither fully part of the galaxy nor fully ejected. It orbits slowly. Some of it will eventually fall back. Some will escape forever. It is a reservoir, a buffer zone, a cosmic junkyard of recycled material. Gas ejected by supernovae flows into this medium. It is hot, ionized, difficult to detect, but over billions of years, the accumulated mass could be enormous, enough to account for the missing baryons. Observing this gas requires X-ray telescopes. The hot gas emits X-rays, but the signal is faint, spread across huge areas of sky. Separating it from background noise is challenging. Recent surveys using the Chandra X-ray Observatory and XMM Newton found evidence of this hot halo, extended emission around the Milky Way, exactly where theory predicted. The mass estimates are uncertain. Maybe 50 billion solar masses, maybe 100 billion. Definitely not enough to account for all the missing baryons, but a significant chunk. Where is the rest? Nobody knows. Some might be in cold molecular clouds too dark to see. Some might be in rogue planets and brown dwarfs scattered through the halo. Some might have been ejected entirely, now floating in intergalactic space far beyond our reach. The James Webb observations are crucial. Webb sees infrared light. It can detect warm gas at intermediate temperatures. too cool to emit X-rays, too warm to be molecular clouds. This warm gas might contain enormous mass. Previous instruments could not see it. Webb can. Early results are promising, but incomplete. Webb found patches of warm gas in the outer halo. More than expected, but mapping the entire halo takes time. Each observation covers a small area. Building a complete picture requires years of data collection. By now we have seen the galaxy is larger than thought, heavier than measured, and missing more matter than we realized. Each discovery reveals deeper layers of mystery. The more we learn, the more questions emerge. The missing baryon problem is not unique to the Milky Way. Other galaxies have the same issue. Half their baryons are unaccounted for. This suggests a universal process. Something about galaxy formation leaves baryons in hard-to-detect states or locations. Maybe this is normal. Maybe galaxies always lose or hide half their matter. Maybe the neat budget we expect does not reflect reality. The universe is messier than our models predict. Matter flows, cycles, hides, and we struggle to track it all. Finding the missing baryons matters for more than accounting. It affects our understanding of galaxy evolution, star formation rates, chemical enrichment, feedback processes. Everything connects. You cannot model a galaxy correctly if you're missing half the ingredients. The search continues. Better instruments, deeper observations, more creative detection methods. Somewhere 200 billion solar masses of normal matter are waiting, and eventually we will find them. Missing matter, hidden structure, strange velocities. The Milky Way keeps revealing complications. But the biggest question remains: where does our galaxy truly end? Draw a line marking the edge of the galaxy. Sounds simple? It is impossible. Galaxies do not have boundaries like countries or continents. No border wall, no sign saying, "Now leaving the Milky Way." Stars just thin out, gradually, slowly, until there are none, or maybe a few scattered stragglers. Where exactly does that become not the galaxy? This is not a philosophical question. It is a practical problem. Astronomers need a definition, a standard measurement, a way to compare galaxies. But nature does not cooperate. The universe does not care about our need for clean categories. Several definitions exist, none of them perfect. The optical radius marks where visible stars become too faint to see. This gives you the bright disk, the obvious part. For the Milky Way, approximately 100,000 light years. But this ignores all the faint stars, dim dwarfs, scattered halo objects. It is like measuring a city by counting skyscrapers and ignoring all the houses. The virial radius is more scientific. It marks where objects are gravitationally bound to the galaxy. Inside this radius, stars orbit the center. Outside, they drift freely. For the Milky Way, this gives about 250,000 light years. Much better. But even this has problems. Some stars outside the virial radius still move with the galaxy. They share our motion through space. They formed here. Are they part of the galaxy or not? The virial radius says no. Common sense says maybe. Then there is the dark matter halo. It extends far beyond everything else. If the halo reaches 400,000 light years out, is that the real edge? Most astronomers say no. The halo fades so gradually that choosing any boundary is arbitrary. It is like trying to mark where Earth's atmosphere ends. Technically, it extends thousands of miles up. Atmospheric particles exist at the altitude where the International Space Station orbits. Higher still, individual atoms drift in near vacuum. At what altitude does atmosphere become space? We draw the line at the Kármán line, 100 kilometers up. But that is a human convention, a useful definition, not a physical boundary. Air pressure drops smoothly from sea level to vacuum. No sharp edge exists. The Milky Way works the same way. Star density is highest at the center. About 1 million stars per cubic light year. Move outward toward the solar neighborhood. 10 stars per cubic light year. Farther still, 1 star per 10 cubic light years. At the edge of the halo, 1 star per 1,000 light years. Keep going. Eventually, you reach 1 star per million light years, per billion, per trillion. The numbers shrink towards zero, but never quite reach it. Somewhere out there, isolated stars drift alone. Rogue objects ejected from the galaxy, but not quite in intergalactic space. Do they count as Milky Way stars? Depends on your definition. Dark matter creates the same problem. The halo extends far beyond visible stars. How far? Models suggest at least 250,000 light years. That is the virial radius, where material is gravitationally bound. But some models push the halo to 400,000 light years. Others suggest 600,000. Some calculations extend it past 1 million light years. A million light years. If true, that makes the Milky Way 20 times wider than the old textbook measurements. 20 times more space under our gravitational control. Picture the scale. Andromeda sits 5 million light years away. If our dark matter halo reaches 1 million light years out, and Andromeda's halo does the same, only 500,000 light years of truly empty space separates us. The halos might already be touching. 2 invisible clouds of dark matter, interpenetrating, mixing, preparing for the eventual collision. We cannot see the halo directly. Dark matter does not emit light, does not absorb light, does not interact with electromagnetic radiation at all. It only interacts through gravity. But that gravity is real, measurable, powerful. Researchers map the halo using indirect methods. Satellite galaxy orbits reveal where mass concentrates. Gravitational lensing shows where space curves. Computer simulations predict how dark matter should distribute based on galaxy formation models. You are inside the halo right now. Dark matter surrounds you, passes through you. Earth swims through a sea of dark matter particles, moving at hundreds of miles per second. Trillions stream through your body every second. You feel nothing. They pass through normal matter like ghosts. If the halo truly extends 1 million light years, the Milky Way claims an enormous volume of space. Most of the local group falls within our sphere of influence. We are not just a galaxy, we are a galactic empire, a superstructure of invisible mass dominating everything around us. Gas clouds blur boundaries further. The Milky Way produces galactic winds. Supernova explosions blow material outward. This gas travels hundreds of thousands of light years before dispersing. Is that gas part of the galaxy? It came from here. It will eventually fall back. But right now it exists far beyond any reasonable boundary. The Magellanic Stream illustrates this problem perfectly. Gas, stripped from the Magellanic Clouds, forms a stream across the sky, about 600,000 light years long. This gas is not part of the Magellanic Clouds anymore. It is not part of the Milky Way yet. It exists in limbo, transitional space, like the shoreline where ocean meets beach. Where does the ocean end? Where the water stops, but waves wash up the sand. Spray carries salt inland. The boundary blurs. Satellite galaxies add more confusion. They orbit the Milky Way, but are considered separate objects. Why they have their own stars, their own structure, but they are gravitationally bound to us. They will eventually merge with us. Are they part of the Milky Way or not? Both answers work, depending on context. The virial radius tries to solve this problem. It defines the boundary where objects are gravitationally bound. Inside this radius, everything orbits together. Outside objects drift independently. For the Milky Way, this gives about 250,000 light years. A clean number, a definite boundary. Except it is not that clean. Objects outside the virial radius can still feel the Milky Way's gravity, weak gravity, not strong enough to maintain orbits, but present, measurable, influential. The gravitational field extends indefinitely, fading, never stopping. Light from the Milky Way travels forever. The photons keep moving. They carry information about our galaxy across the universe. In that sense, the Milky Way's influence is infinite. Every star that ever shone here sent light in all directions. That light is still traveling, marking our presence across cosmic distances. Like friendship boundaries, you cannot draw a clear line separating close friends from acquaintances. Relationships blur. Some people are clearly inner circle, others clearly strangers, but many fall in between. You care about them, see them occasionally, would help if they asked, but are they close friends? The boundary is fuzzy, undefined. Here is what this means practically. When you measure the Milky Way size, you are making a choice, choosing a definition, deciding what counts and what does not. The 200,000 light-year measurement uses the virial radius. Reasonable, defensible, but not absolute truth. Another astronomer might use a different definition, where star density drops below a threshold, or where dark matter fades to a certain level, or where satellite galaxies stop orbiting. Each definition gives a different size. None of them wrong, none of them perfectly right. The galaxy has no edge because the universe is continuous. Matter distributes smoothly. Density gradients slope gently. Boundaries are human constructs imposed on a cosmos that does not care about categories. We live in a galaxy that fades into nothing. No walls, no boundaries, no clear end. Just a slow transition from dense to empty, from here to nowhere. And measuring that transition is harder than measuring the galaxy itself. Earth's atmosphere provides a perfect analogy. Ask, where does the atmosphere end? And you get different answers. Commercial aircraft fly around 30,000 feet, still plenty of air. The ozone layer peaks around 100,000 feet. Atmospheric molecules exist there. The ISS orbits at 250 miles. Atmospheric drag still affects it. Individual hydrogen atoms drift at 6,000 miles altitude. Still technically atmosphere. The Van Allen radiation belts extend to 36,000 miles. Particles trapped by Earth's magnetic field. Part of Earth's system, but not really atmosphere. Where does it end? We draw arbitrary lines. The Kármán line at 62 miles. The exosphere boundary at 6,200 miles. Each serves different purposes. None represents a physical edge. The Milky Way faces the same ambiguity multiplied by cosmic scale. Andromeda's edge approaching ours creates fascinating complications. If both dark matter halos extend 1 million light years, they might already overlap. A shared zone. Territory claimed by both galaxies. Rogue stars in this region feel gravitational pulls from two directions. They might orbit in complex patterns. figure-8 trajectories around both galactic centers, or chaotic paths switching allegiance over time. Eventually, the halos will merge completely. The distinction between our dark matter and their dark matter becomes meaningless. One combined halo, one gravitational field. The collision will have begun long before the visible disks touch. Rogue stars, drifting in the no man's land between galaxies, face uncertain futures. Some will be captured by the Milky Way, others by Andromeda. Some will be flung into true intergalactic space during the merger. Cosmic refugees with no home. The lack of clear boundaries matters for more than academic definitions. It affects how we count galaxies, how we measure their properties, how we compare them. If every galaxy is twice as large as measured with fuzzy, undefined edges blending into neighbors, the whole concept of separate galaxies becomes questionable. Maybe galaxies are not discrete objects. Maybe they are density peaks in a continuous cosmic web, concentrations of matter connected by filaments. The visible parts are just the brightest nodes. The real structure extends everywhere, interconnected, continuous. We impose categories because human minds work that way. We see distinct objects, separate things, but the universe might not work that way. It might be one continuous field of matter and energy, varying in density, flowing, mixing, no boundaries, just gradients. And as you drift towards sleep tonight, consider this. The galaxy fades into darkness the same way you fade into sleep. No clear moment, no definite boundary. You are awake, then drowsy, then dreaming. When exactly did sleep begin? You cannot pinpoint it. Consciousness dims gradually, thoughts slow, reality blurs. The Milky Way is the same. It is bright here, dimmer there, eventually dark. But the transition is gentle, smooth, like sliding into sleep. And just as sleep contains dreams, mysterious and half-remembered, the outer galaxy contains mysteries we are only beginning to glimpse. Let the edges blur. Let the boundaries fade. 200,000 light years, or 250,000, or more. The exact number matters less than understanding this. Our home is vast, fuzzy-edged, continuous with the cosmos, and beautiful beyond measure. Rest now. The galaxy will still be here tomorrow. Undefined edges and all. The Milky Way is a cannibal. Our galaxy grew to its current size by eating others. Hundreds of smaller galaxies fell into our gravitational well, got torn apart, devoured. Their stars became ours. This is how galaxies grow, not through slow accumulation, through violence, galactic mergers and cannibalism. Bigger galaxies eat smaller ones. The strong dominate. The weak become meals. Survival of the gravitationally massive. Evidence of these ancient meals surrounds us. Stellar streams wrap around the galaxy. Each stream is a corpse. A dwarf galaxy that got too close. The Milky Way ripped it apart, stretching its stars into long ribbons. These ribbons orbit for billions of years before dispersing completely. The Sagittarius dwarf is being eaten right now. Active consumption. We caught it in the act. The dwarf contains about 400 million stars. Over the next billion years, those stars will scatter across the Milky Way. In 2 billion years, no trace of Sagittarius dwarf will remain except ghosts in the data. But Sagittarius is just the latest victim. The galaxy has fed many times before. Gaia Enceladus was a major meal. About 10 billion years ago, a galaxy 1/4 the Milky Way's mass collided with us. This was not a minor dwarf. This was a substantial galaxy. The collision was violent, Both galaxies suffered, but the Milky Way won. We absorbed Gaia Enceladus completely. Its stars now populate our halo, billions of them, former citizens of a destroyed civilization. The Gaia spacecraft detected this ancient merger by studying star motions. Stars from Gaia Enceladus orbit differently than native Milky Way stars. They move in retrograde directions, tilted orbits, eccentric paths. Their motion betrays their foreign origin. Chemical analysis confirms it. Gaia Enceladus stars have different compositions than native stars, less heavy elements, different abundance patterns. They formed in a different galaxy with a different chemical history. Now they orbit here, captured, assimilated, ours. The Kraken merger came even earlier, 11 billion years ago. An even more massive collision. Kraken might have been half the Milky Way's mass at that time. The merger reshaped our galaxy, triggered intense star formation, built much of our current disk structure. Kraken's remains are harder to identify because they are so thoroughly mixed. But they are there, billions of stars, integrated into our structure, indistinguishable from native stars without careful chemical and kinematic analysis. Scientists identify merger remnants through multiple methods. Star velocities reveal orbital patterns inconsistent with smooth disk formation. Chemical compositions show signatures from different environments. Ages cluster around merger times when star formation exploded. Computer simulations rewind galactic history, input current positions and velocities, run time backward, watch the galaxy disassemble. Streams coalesce into their parent dwarfs. Major mergers reverse. The Milky Way shrinks. These simulations reveal a violent past. Dozens of mergers, hundreds of smaller accretions. Each merger left scars, tidal streams, stellar shells, disrupted orbits. The halo is a graveyard. Every star there came from somewhere else, captured during ancient collisions. The disk contains immigrants too, stars stirred up during major mergers, mixed into the rotating structure. You are made from star stuff. Carl Sagan said that. Every atom in your body formed inside stars. But those stars came from galaxies that no longer exist. Galaxies the Milky Way destroyed. The iron in your blood, the calcium in your bones, the carbon in your cells. Forged in stars that once belonged to Gaia Enceladus, or Kraken, or Sagittarius, or dozens of other victims, you are partly alien, made from material from conquered galaxies. The Sequoia Dwarf, the Helmi Streams, Omega Centauri, all merger remnants. Omega Centauri is particularly interesting. It is the largest globular cluster orbiting the Milky Way. Contains about 10 million stars, but it is too massive for a normal globular cluster. Too chemically complex. Some researchers propose it is the surviving core of a destroyed dwarf galaxy, the nucleus that remained intact after the Milky Way stripped away the outer stars. If true, Omega Centauri is a refugee, the sole survivor of a galactic massacre. Everything else scattered, absorbed, gone. Only the densest core escaped complete dissolution. The Magellanic Clouds will be eaten. Sagittarius is being digested. Smaller dwarfs orbit too close. Doomed. In the future, Andromeda will collide with us. That will be the final meal. The merger that transforms us completely. Galactic cannibalism explains why big galaxies keep growing. The rich get richer. Once you are massive enough, your gravity reaches farther. You can capture more victims, eat them, grow larger. Your increased size lets you capture even more victims. Positive feedback, runaway growth. The rich get richer. Galaxy Edition. Except instead of wealth, it is mass. And instead of business acquisitions, it is violent gravitational shredding. And there are no antitrust laws to stop it. Dwarf galaxies have it rough. They are prey, constantly threatened by larger neighbors. Most of them eventually get eaten. Only a few survive in isolation. The Milky Way dominated the local group by eating everything within reach. We built an empire through consumption. But here is the strange part. Those devoured galaxies are not gone. Their stars still exist, still shine, still orbit. They just orbit us now. The Milky Way is not a single entity. It is a collective, a graveyard empire built from the corpses of dozens of smaller galaxies. The timeline of major mergers reveals the pattern. 11 billion years ago, Kraken merged. 10 billion years ago, Gaia and Enceladus. 8 billion years ago, several smaller dwarfs. 5 billion years ago, another wave of accretions. 2 billion years ago, Sagittarius started its death spiral. The mergers never stopped. The Milky Way has been eating continuously since its formation. Future meals are already identified. The Magellanic Clouds will be consumed in 2 to 3 billion years. Several ultra-faint dwarfs orbit too close. Their fates are sealed. Tidal forces are already pulling them apart. Within 5 billion years, they will be gone, scattered, absorbed, added to our collection. Chemical signatures in stars are like fingerprints. Each galaxy has a unique chemical evolution, different ratios of elements, different enrichment histories. When the Milky Way absorbs a dwarf galaxy, the stars retain their chemical signatures. We can identify them billions of years later. The European Southern Observatory's survey analyzed hundreds of thousands of stars, measured their chemical compositions precisely, identified distinct populations, native disk stars, thick disk stars from early mergers, halo stars from Gaia and Enceladus, Sagittarius stream stars, each group chemically distinct. This is forensic astronomy, crime scene investigation on a galactic scale. The evidence is scattered, billions of years old. But careful analysis reveals the truth. The Milky Way is a serial killer. Dozens of victims, and we are standing on the evidence. The emotional weight of this is profound. Look up at the night sky. Many of these stars are not native to the Milky Way. They were captured, stolen from galaxies that no longer exist. They orbit here not by choice, but by force. Gravitational prisoners in a structure built through violence. And you, made of atoms from those destroyed galaxies, you carry their legacy in every cell. The calcium strengthening your skeleton formed in a star that once belonged to Kraken. The oxygen you breathe came from a supernova in Gaia Enceladus. You are a monument to galactic cannibalism, walking evidence of ancient violence. This is how structure forms in the universe, not peacefully, not through gentle accumulation, through collision, merger, destruction. The beautiful spiral galaxy we call home is built on the graves of hundreds of smaller galaxies, an empire forged through conquest. The past is violent. The future promises more violence. Andromeda approaches. The collision is inevitable, and the timeline just got shorter. Andromeda is coming. This is not a theory. This is confirmed fact. Our neighboring galaxy is racing toward us at 70 miles per second. The collision is inevitable. For decades, scientists calculated the impact would happen in approximately 4.5 billion years. Mark your calendars. except those calculations assumed the old galactic sizes: smaller Milky Way, smaller gravitational reach, more space between us and Andromeda. A bigger Milky Way changes the timeline. Gravity reaches farther. The galaxies will start pulling on each other sooner than predicted. Their massive dark matter halos will interact first, stretching hundreds of thousands of light years outward. When those halos touch, the collision begins. Think of two people walking toward each other. If they are both larger than you, thought they bump into each other sooner. Same principle. Galactic scale. New models suggest the interaction could begin in under 4 billion years, maybe 3.5 billion. The exact timeline depends on precise measurements we are still collecting, but the trend is clear. Bigger galaxies mean earlier contact. Here is what happens during a galactic collision. First, the outer halos start merging, dark matter interpenetrating. This phase is invisible, but gravitationally intense. Stars feel the pull from both galactic centers. Orbits destabilize. Some stars get flung into intergalactic space. Others plunge toward the cores. Then the visible disks collide. Not a crash. More like two clouds passing through each other. Stars are so far apart that direct impacts are incredibly rare. You could fit millions of Earths between neighboring stars. The chance of the sun hitting another star during the merger is essentially zero, but the gravitational chaos is real. Star formation explodes. Gas clouds compress. New stars ignite across both galaxies. The Milky Way and Andromeda will orbit each other multiple times, dancing, spiraling. Each pass strips away more material. Tidal forces shred the spiral arms. Stellar streams scatter in every direction. The once elegant structures become warped, distorted, unrecognizable. Eventually, maybe 1 billion years after first contact, the galaxies merge completely. The result is a massive elliptical galaxy. No more spiral arms, no more organized disk, just a blob of 4 trillion stars orbiting in random directions. Astronomers already named this future galaxy Milkomeda, cute name for the death of 2 ancient spirals. But here is the critical question. Will Earth survive? Will the Sun survive? Will humanity be around to see it? Good news first. The Sun will likely survive the merger. It sits far enough from the galactic center that it will probably avoid the most violent regions. Earth might get flung into a different orbit or ejected entirely into intergalactic space, or stay roughly where it is. The odds favor survival. Bad news. The Sun will be long dead by then. Our star has about 5 billion years of fuel left. The Andromeda collision happens before the Sun dies, but barely. We might get a front row seat to the early stages. A bigger Milky Way moved up that timeline. The show starts sooner. And here's the part nobody talks about. What if Andromeda is also bigger than we measured? Their estimates could be wrong too. If both galaxies are larger, the collision happens even sooner. The gravitational chaos becomes more intense. The final merged galaxy becomes even more massive. We are already seeing the early signs. Andromeda's halo extends toward us. Our halo reaches toward them. The halos might already be touching. The collision might have already begun, slowly, invisibly, in the dark matter enveloping both galaxies. 4 billion years sounds like forever, but on cosmic timescales, it is tomorrow, and tomorrow just got a little closer. Imagine watching the night sky as Andromeda approaches. Right now it appears as a faint smudge, barely visible to the naked eye. a blur of light 2.5 million light years away. In 1 billion years, it will be noticeably larger. A distinct spiral, visible across the sky, bright enough to cast shadows on moonless nights. In 2 billion years, it will dominate the heavens, a massive spiral stretching across a third of the visible sky, its spiral arms clear and beautiful. You could see individual star-forming regions, nebulae glowing red and blue. In 3 billion years, it will fill half the sky. Overwhelming, magnificent, terrifying. The spiral structure will start to distort as tidal forces take hold, arms stretching, fragmenting. In 4 billion years, first contact. The visible disks begin to interpenetrate. The sky will explode with new stars. Regions of intense star formation lighting up across both galaxies. The night will never be truly dark again. Too many young bright stars, like watching 2 hurricanes merge on satellite imagery. Slow, inevitable, beautiful, destructive. The spiral patterns swirling into each other. Structures that took billions of years to form, destroyed in a cosmic instant. Computer simulations show the process in detail. The first pass brings the galaxies close, but not merging. They swing past each other. Gravitational interaction slows them, changes their orbits. They separate. Then gravity pulls them back together. The second pass brings them closer. More tidal stripping. More stars flung into space. More gravitational chaos. The third pass might achieve merger. Or maybe it takes a fourth, fifth. Each orbit brings them closer. Each interaction dissipates orbital energy. Eventually, they cannot escape each other. They spiral inward, merge. The fate of satellite galaxies caught in the middle is grim. The Magellanic Clouds, Triangulum, dozens of dwarf galaxies, all orbiting in the space between the Milky Way and Andromeda. When the giants collide, these dwarfs get caught in the crossfire. Some will be shredded by tidal forces, torn apart by competing gravitational pulls, their stars scattered across the merger remnant. Others will be flung out entirely, ejected at high velocities, cast into intergalactic space to wander alone. A few might survive intact, captured into orbit around the merged galaxy, battered, stripped of outer stars, but alive. Triangulum faces a particularly uncertain fate. It is the third largest galaxy in the local group, big enough to affect the merger dynamics. Some simulations show it colliding with Andromeda before the main Milky Way Andromeda merger, a 3-way collision instead of 2-way. This would make the final result even more chaotic, even more massive. The Sun will likely survive, but its orbit will change. Currently, we circle the galactic center once every 230 million years. A nice, stable orbit. After the merger, our orbit could be anything. Highly elliptical, plunging close to the core, then swinging far out. Or we might get flung into the outer halo, orbiting in the suburbs of Milkomeda. Earth's fate is tied to the Sun's. If the Sun survives, Earth probably survives. But survive is relative. The night sky will be completely different. The constellations erased. New patterns formed from different stars. If we are flung into intergalactic space, the sky might be nearly empty, dark, lonely, just the glow of distant galaxy clusters. But remember, the Sun will already be dying by then. In about 1 billion years, the Sun will heat up as its core fuses more hydrogen. Earth's oceans will boil away. The planet will become uninhabitable. Long before the Andromeda collision reaches its peak, Earth will already be dead. Unless humanity survives, unless we spread to other star systems, other galaxies, If our descendants are still around 4 billion years from now, they will witness the most spectacular cosmic event imaginable: the collision of two giant galaxies, the birth of Milkomeda. They might watch from a safe distance, from a planet orbiting a star in a different galaxy, looking back at the Milky Way and Andromeda as they dance and merge, watching their ancestral home transformed. Or maybe they will be there, riding it out, adapting, surviving. Humans are good at that. The collision is coming. The timeline shortened. The show starts soon. On cosmic scales, we are living in the last moments before impact, the calm before the storm, and the storm, when it arrives, will reshape the local universe. Andromeda promises future violence. But the collision raises another question. In a galaxy twice as large, with double the stars and double the planets, are we alone? 400 billion stars, 400 billion opportunities for planets, 400 billion chances for life. More stars means more planets, means more habitable zones. Conservative estimates suggest 60% of stars have planets. That gives us 240 billion planetary systems. Maybe 10% orbit in the habitable zone where liquid water can exist. 24 billion potentially habitable planets, doubled from previous estimates. Even if life is rare, 1 in 1,000 habitable planets, that still gives us 24 million living worlds in the Milky Way alone. 24 million planets where biology exists, where cells divide, where evolution operates, where organisms adapt and survive. Even if intelligent life is extraordinarily rare, 1 in a million among living worlds, that gives us 24 intelligent species in our galaxy. Maybe more, maybe less. The numbers are uncertain, but doubling the galaxy size doubled the probability. The Drake equation just changed. Every variable increased. Number of stars, fraction with planets, number of habitable zones. The probability of finding alien life went up significantly. But here is where it gets haunting. 400 billion stars. Double chances for life. Where is everybody? The Fermi paradox intensifies. If there are so many chances for life, so many potential civilizations, why no signals? Why no alien probes? Why does the galaxy seem empty? We have been listening for decades. SETI, the search for extraterrestrial intelligence, has scanned approximately 100,000 stars so far. Under the old model, that represented 0.05% of the galaxy. Now, it represents only 0.025%. We have barely begun searching. The task just doubled. Current SETI efforts use radio telescopes to scan the sky for artificial signals, narrow band emissions that nature cannot produce, repeating patterns, mathematical sequences, anything suggesting intelligence. So far, nothing. Silence. The galaxy appears empty, but we have only searched a tiny fraction. It is like dipping a cup into the ocean and concluding there are no fish because you caught none in that cup. The ocean is vast. The cup is small. The James Webb Space Telescope is taking a different approach. Instead of listening for signals, it is looking for biosignatures, chemical signs of life in exoplanet atmospheres. Oxygen and methane together suggest biological processes. On Earth, these gases coexist only because life produces them. Without life, they would react and disappear. Webb is studying exoplanet atmospheres when they pass in front of their stars. The starlight filters through the atmosphere. Different molecules absorb different wavelengths. By analyzing the spectrum, we can detect what gases are present. The original target list included approximately 1,000 planets. Now, astronomers realize there are twice as many candidate systems. Each star could have multiple planets. Priority targets need reevaluation, more work, but more opportunities. Several exoplanets already show promise. TRAPPIST-1 system has 7 Earth-sized planets. 3 orbit in the habitable zone. Proxima Centauri b orbits the nearest star to our Sun, potentially habitable. Dozens of others discovered recently. Each discovery raises hope. Each one might harbor life. But detecting biosignatures is difficult. Atmospheres are thin. Signals are faint. Separating biological signatures from geological ones is challenging. The Great Filter Theory offers one explanation for the silence. It proposes a barrier preventing civilizations from becoming spacefaring. Either the filter is behind us, meaning life itself is incredibly rare, or the filter is ahead of us, meaning civilizations tend to self-destruct before achieving interstellar communication. If the filter is behind us, we got lucky. Life emerging is the hard part. Intelligence developing is the hard part. We passed the test, but that means we might be alone. One of very few civilizations in the galaxy. If the filter is ahead, we are doomed. Every civilization reaches a point where it destroys itself. Nuclear war, climate collapse, artificial intelligence gone wrong. We are heading toward the filter right now, and the silence suggests most civilizations do not survive it. Other theories exist. Maybe intelligence is rarer than we think. Maybe we are one of very few. Maybe technological civilizations exist for only brief periods, a few thousand years. Compared to the age of the galaxy, that is nothing. 2 civilizations would need to exist at the same time to communicate. The odds drop dramatically. Or maybe they are there but not communicating. Maybe they are listening like us. Everyone waiting for someone else to transmit first. A galaxy full of civilizations, all silent, all waiting. Or maybe we are listening the wrong way, using radio telescopes for signals that advanced civilizations abandoned millennia ago, like searching for Morse code in a world that uses fiber optics. 400 billion stars, and we have not heard hello from anyone. The silence is deafening. Either we are alone, or everyone else is hiding, or we are not listening correctly. But here is the hopeful turn. The odds just doubled. Double the stars, double the planets, double the chances. Someone might be out there, looking up at their sky, wondering the same questions, feeling the same loneliness, hoping for contact. SETI continues searching. New telescopes come online. The Allen Telescope Array, FAST in China, the Square Kilometer Array under construction, each more sensitive than the last, each capable of detecting fainter signals from farther away. We are getting better at finding exoplanets. The Kepler mission discovered thousands. TESS is finding more. Webb is characterizing their atmospheres. Each advancement brings us closer to answering the question, are we alone? The bigger galaxy means more places to search, but also more hope, more opportunities, greater probability that somewhere orbiting one of those 400 billion stars, life exists. Maybe simple, maybe complex, maybe intelligent, and maybe they are looking for us too. The search for life continues in our newly enlarged home. But this discovery affects more than just the Milky Way. If we got our galaxy wrong, what about all the others? If the Milky Way is twice as large, as measured every other galaxy, needs remeasurement. This is the terrifying implication, the realization that makes cosmologists stay up at night recalculating everything they thought they knew. The cosmic census needs rewriting. Researchers tested the hypothesis. They selected nearby spiral galaxies, Andromeda, Triangulum, galaxies close enough for detailed observation. Then they applied the new measurement techniques: satellite galaxy tracking, stellar stream mapping, dark matter halo calculations. Every single galaxy came back larger, not just a little, significantly, 50% bigger on average. Some doubled in size just like the Milky Way. Andromeda grew from 220,000 light-years to over 300,000 light-years. Triangulum expanded from 60,000 to nearly 100,000. Every major galaxy examined came back larger. The pattern is universal. We systematically underestimated spiral galaxy sizes across the board. Remember the shock from episode 1? We got our own galaxy catastrophically wrong. Now multiply that shock by every galaxy in the universe. Billions of galaxies, all larger than recorded. The entire cosmic map needs redrawing. This changes everything: how we measure distances, how we calculate masses, how we understand structure formation. Every equation built on galaxy sizes now crumbles. Galaxy masses determine how they interact. Bigger galaxies have stronger gravity. They strip stars from smaller neighbors more easily. They dominate their local groups more completely. They form clusters differently. Recalculate masses, and you recalculate galaxy evolution. The universe becomes denser, more crowded. Galaxy collision rates increase. The space between galaxies is smaller than thought. Gravitational influences reach farther. The cosmic web tightens. Like discovering every ruler you ever used was missing half its length. Every measurement you made was wrong. Every calculation based on these measurements needs revision. The foundation shifted. Everything built on it becomes uncertain. Distance measurements become problematic. Astronomers use certain types of galaxies as standard candles. Objects with known brightness measure how bright they appear, calculate how far away they must be. But if those galaxies are bigger, their brightness changes, the distances change, the expansion rate of the universe changes. Dark energy measurements depend on precise distance calculations. Dark energy is the mysterious force accelerating cosmic expansion. We measure it by observing how fast distant galaxies recede. But those measurements assume we know galaxy properties correctly. If galaxies are universally larger, dark energy calculations shift. The Hubble tension gets worse. This is the disagreement between different methods of measuring the universe's expansion rate. Local measurements using supernovae give one answer. Cosmic microwave background measurements give another. The discrepancy is already troubling. Now, with galaxy sizes doubled, it grows larger. Either our local measurements are more wrong than we thought, or our early universe measurements are wrong, or something fundamental about cosmology needs revision. Baryon acoustic oscillations serve as cosmic rulers, ripples in the distribution of galaxies frozen from the early universe. Cosmologists use them to measure distances, but the ripples depend on galaxy clustering. How many galaxies? How massive they are? How they distribute? If galaxies are bigger and more massive, the clustering changes. The ripples shift. The ruler gets adjusted. Every measurement method connects. Change one, and you affect all the others. The cosmic distance ladder has many rungs. Each depends on the one below it. If the bottom rungs are wrong, every measurement above them is wrong. We might have been climbing the wrong ladder for decades. Computer simulations predicted galaxy formation, how structure emerged from the smooth early universe, how dark matter clumped, how gas cooled and formed stars. These simulations used galaxy sizes as benchmarks. If the benchmarks are wrong, the simulations are wrong. Everything needs rerunning with correct parameters. The implications cascade through cosmology, Big Bang models, dark matter distributions, dark energy equations, structure formation timelines. Everything connects to galaxy properties. Change the galaxies, and you change the universe. Some cosmologists are excited. This explains long-standing problems. The missing satellite problem, for example. Simulations predict large galaxies should have hundreds of satellites. We only observe dozens. If our galaxy is bigger, its gravity pulls farther. Maybe those missing satellites exist, but orbit so far out we have not found them yet. Others are worried. If we got something this fundamental wrong, what else did we miss? How many other assumptions need questioning? The James Webb Space Telescope is observing the earliest galaxies from when the universe was only a few 100 million years old. These galaxies appear surprisingly large and mature, too large for the time available to form them. This has been called the impossible early galaxy problem. But maybe it is not impossible. Maybe early galaxies were larger than we calculated using our flawed methods. Maybe the problem disappears when we apply correct measurements. Or maybe it gets worse. We do not know yet. The philosophical implications run deep. We thought we understood the universe's large-scale structure. Galaxies, clusters, superclusters, the cosmic web. But if every galaxy is twice as large, the web is denser, more connected, less empty space, more gravitational interaction. The universe might be more violent than we thought. More collisions, more mergers, more chaos. Structure formation happened faster, earlier, more intensely. We measured the universe wrong. Not slightly wrong, fundamentally wrong. And now we face the enormous task of remeasuring everything. Every galaxy, every cluster, every cosmological parameter. It will take decades, maybe longer. But that is science. Not about being right forever. About correcting yourself when evidence demands it. About having the humility to admit mistakes and start over. The universe just got bigger, denser, more complex, and more mysterious. We remeasure the universe, we search for life, we watch Andromeda approach. But through it all, one question remains. What have we truly learned? 200,000 light years. That is the current best answer. Not the final answer, just the best we have right now. In 10 years, the number will change. Better telescopes, better data, better understanding. The measurement will improve. It always does. Future telescopes will refine our knowledge. The Nancy Grace. Roman space. Telescope launches soon. Designed to survey huge areas of sky with incredible depth. It will find faint satellites, map distant stellar streams, measure gravitational lensing across wide fields. Each dataset will refine our model of the Milky Way. The extremely large telescope will help too, a ground-based giant with a mirror over 100 feet across, resolving power beyond anything built before. It will observe individual stars in satellite galaxies, measure their velocities precisely. Each measurement tightens constraints on galactic mass and size. The number will change. 200,000 light years, might become 220,000, or 180,000, or 250,000. The uncertainty will shrink, confidence will increase. But the number will never be perfect, never final, just progressively better. We live in a galaxy we are still measuring, a structure so large it defies complete observation. We sit inside it, trying to map it, knowing our view is limited, incomplete, biased by our location. This is a humility lesson for science, for humanity. We thought we knew our home. We were confident. 70 years of measurements, thousands of papers, consensus, and we were wrong. Always question, always verify. No measurement is truly final. The universe constantly surprises us. The more we learn, the more we realize we do not know. But that is not depressing. That is exciting. There is always more to discover, always deeper mysteries, always new revelations waiting. Your children will learn different numbers in school, larger, more accurate. They will study the Milky Way as a 200,000 light-year galaxy with 400 billion stars. These will be facts as basic as Earth orbiting the Sun, and they will wonder how we got it so wrong for so long. We will tell them we measured from inside. We did the best we could with the tools we had, and when better tools arrived, we corrected our mistake. That is science. Knowledge grows. Tools improve. Understanding deepens. The next generation will know more than we do. Their children will know even more. Progress is not smooth, not linear, but it happens. Bigger home means more to explore, more mysteries to solve, more questions to answer. The galaxy doubled in size. Our wonder should double too. We are small, incredibly small, sitting on a rock orbiting an average star in the outer suburbs of a giant galaxy. One of 400 billion stars, one of trillions of planets, insignificant on cosmic scales. But we figured it out. We, these tiny specks, these brief flickers of consciousness, measured the invisible scaffolding holding our galaxy together. We discovered we were wrong and had the courage to admit it. We looked at evidence that contradicted 70 years of consensus and said, we need to change our minds. That is impressive. We are small, but we figured out we are small. We are brief, but we measured timescales of billions of years. We are limited, but we detected the infinite. The Milky Way is vast, 200,000 light years wide, 400 billion stars, 4 trillion solar masses, most of it invisible, most of it mysterious, most of it still waiting to be understood. And we live here, swimming through dark matter we cannot feel, orbiting in spiral arms we cannot see from outside, surrounded by the remnants of devoured galaxies, heading toward a collision with Andromeda, searching for life among billions of planets. Home is bigger than we thought, stranger than we imagined, more violent, more beautiful, more mysterious than 70 years of astronomy suggested. But it is still home, and we are still here, learning, measuring, questioning, discovering. The story of how we got the Milky Way wrong is not a story of failure. It is a story of progress. We made the best measurements we could. Then we made better ones. We will make even better ones tomorrow. That is the human story, reaching beyond our grasp, asking questions bigger than ourselves, building tools to see farther, deeper, clearer, never satisfied, always curious, always wondering what comes next. And tonight, as you drift into sleep, carry this thought with you. You live in a galaxy twice as large as yesterday. 400 billion suns are shining in the darkness, each one a world unto itself, each one with its own story. Somewhere on a planet orbiting one of those stars, someone might be lying down, looking up at their sky, wondering if they are alone. Now we know there is double the chance they exist, double the opportunity, double the hope. The galaxy is huge. You are small, but you are part of something so vast and beautiful that 70 years of studying revealed only half of it. Breathe in that wonder. Let it fill you. Let it carry you into dreams as vast as the stars. The Milky Way is 200,000 light years wide, maybe more. We will keep measuring, keep learning, keep discovering, and that is beautiful. Good night. Sleep well. The galaxy will still be here tomorrow, twice as large as yesterday, full of mysteries waiting, full of stars shining, full of possibilities we have not yet imagined. Rest now, in the knowledge that home is bigger, stranger, and more wonderful than we ever knew. The universe surprises us, and we, small as we are, surprise ourselves by understanding it. That is enough. That is everything.